So hello, this video is a demonstration on making a Q-learning program. And for this example, I'm going to use a game, maze running, where the agent is put in a grid-like world. There's obstacles, there's a start and a goal. And the goal for the agent is to reach the goal from the start as fast as possible without hitting any obstacles or going off the grid. So first of all, what is Q-learning? In quick terms, it's basically a off policy. This is a off policy method where we have an exploration policy. For example, epsilon greedy, to learn a greedy policy. And for our exploration policy, yes, we're going to use epsilon greedy. And basically, we're going to first define a reward function. And this is the way we communicate between our desired outcome and the agent. So we're telling it what it's supposed to do. And for the input, it's going to require the previous position, the current position, and the goal position, obstacles, and visited states. First of all, if we do reach the goal, if goal reached, we add 10. If we hit an obstacle, we minus 20. And that's going to be the reward. If we do that, because that's going to be like, that's it. We don't really care about anything else. And then now, if we do not either hit the goal or hit an obstacle, we're going to do something where we find the distance between us and the goal in the previous position and the current position. And if the previous position is like the previous distance, is smaller than the current position, then we get a negative 0.5 reward. And if it's less, so the current distance is less than the previous we add 1. If the current position is invisited, that means we've been to this state before already, we will get a negative 1, else get 1 for exploring. And we're going to, so that's the reward function, and you just return the reward. Now we gotta actually make the maze, and this is the maze creation part. To make the maze, it's really simple. We're actually just making a grid of a Q table where it's like a 4J in range grid size. And then for I, blah blah, and then it's going to be like an IJ tuple, something like that. And then it's equals to 0.0 for action and actions. It's gonna be like a action. So that means for each state there's 4 action states, and those 4 action states is just up, down, left, and right. So that's how you make the cube table. And then also you gotta make the obstacles. And the way we're gonna make the obstacles is just we're gonna randomly X and Y, put an obstacle on X and Y, and then we check if it's possible. So we run a BFS to check whether this new grid, after adding this one obstacle, is possible. And if it is possible, then we just continue until we add enough obstacles. And if it's impossible, then we remove. To make sure that this cannot blow into infinity, we have like a max attempts. but should be, if you're reasonable with the number, then it shouldn't even reach max extents at all. So now, move function, really simple. You just take the xy coordinate from the state, and then if it's up, you know, y plus 1. If it's down, y minus 1, something like that. And then once you're down here, you're going to check if it's outside the grid. Stay at original position. And to do this, make sure you save a original position up here so that you can just go back whenever. And this also can kind of contribute to our reward function, because if it's visited, so that means you go back to the same state, you're going to get a -1 reward. So that means we're actually disencouraging the model from going out the grid and staying where he is. So now, once we have all that, we start training. We basically roll out episodes. This time I chose, I remember, 2,000 episodes, and they run really quick. So even 10,000 is fine. It's not going to take long at all. And then we roll out episodes acting on a exploration policy where we have a epsilon, which is a random, well, no, sorry. We have epsilon as 0.2, and then we initialize as random variable. And if that is less than epsilon, that means 20% probability, and then you choose a random action. Else, with 80% probability, that you choose argmax function. So that means you choose the action that has the highest value in your current state. So you choose the highest state value function, and that comes from your Q table. And in each state there's 4, and you just choose the highest one, and then you just do that. And then now you got to update it. To update, you just take the old Q value, and then you take the old Q value. Let's denote it as OQ, and then OQ plus learning rate alpha times the reward after making that action plus gamma, which is discount, times the future max, argmax, sorry, this, yeah, max of the next state, and then minus the old Q value, and that you assign to the new Q value, the updated one. So that's how it learns, and then every time you keep doing this, it'll just slowly go to the good policies. Now, after you're done with training, you're going to want to plot the grid nicely. And to plot, you're just going to draw a grid with matplotlib. And then observe that there's 1, 2, 3, 4, 5. There's 5 rows, but there are 6 lines. So basically, you just draw horizontal lines, 6 horizontals, and 6 vertical. Or grid size +1, and grid size +1, yep. And then after that, you're gonna just want to say that, yeah. And then this is the goal, the starting state, and then we're just going to do a fill between for obstacles, something like this. And then we're gonna draw a row. Was it a row or something? And it's gonna be just a red line, kind of goes like this. This is red, by the way. That's right. Let me make it red. Red. And then it's gonna be like a dot, dot, dot on each of the places. And yeah, that's the end. And next part is the coding session. So welcome to the coding part. First of all, you're gonna have to import the matplotlib, random collections, numpy, and matplotlib.pyplot. So if you don't have these, just pip install them. I already have them in pip installed. So first of all, you're gonna define the reward function that we already discussed with the inputs as follows, as we said. And it's just going to check if our current position is going to be a goal position, if our current position is going to be inside an obstacle where we give a very low reward. And then we just return that if that's the case. Else, we're just going to do distance calculation, and we check whether the distance between us and the goal has decreased after set move, such that, oh, we're going to reward if we're getting closer, and we're going to discourage that if we're getting further. And to calculate the distance, just take the absolute value between the x and y values. Now I have a few bugs here. First of all, the current position, it shouldn't be current position 0 minus current position 0, that would be 0. Instead, it should be current position minus previous position, goal position, sorry, for both as well, x and y. And if the current distance is lower than the previous distance, which means we have gotten closer, then we're going to add 1 to our reward. Else, we're just going to have the reward minus 0.5. And if our current position is invisited, as we already have gone to this current position, we're going to minus reward for wasting a move. And else, we're going to add a reward if we visited a new state. Add that to the visited and return the reward. Now, check possible inputs as follows. We're going to make a queue such that is a BFS, right? And the queue is if we're in the goal already, then we return true. And if we're in visited, then we're going to continue, which cuts off that queue. And then while the queue is still on, so there's still states to visit or moves to try, you're going to try all the possible moves, up, down, left, right, and you see the nx and ny, which means new x and new y axis. Now here, there's a bug as well, is where it shouldn't be ny smaller or equal than grid size. It should be smaller than grid size. The new position is not in obstacles or in visited, then we're going to append that to the queue for visited states later on. So the states that we're going to visit later. And now we're going to define the grid creation function with grid size, number of obstacles, actions, and max attempts as input. Make the table a dictionary, make the obstacles a set, an empty set, and then you're going to make a table of 2 loops, so a loop for y-axis, a loop for the x-axis, I and j. And then you're going to, for each point, for each coordinate, you're going to have 4 actions, and each of them you're going to initialize with 0.0. So that means you're initializing the state action value. So you're making a queue table. And we're going to have attempts equals 0, so that when we do put a new obstacle, we're going to check whether this is possible. And we're not going to keep checking until infinity. So if it's less than attempts, well, we're going to deal with that later on, but you should just avoid that. If you should be able to avoid that if your number of obstacles is fairly low. So you're going to have x and y randomized as integers, and over here in the elif section, in the if section, this doesn't really matter, but it should be a tuple to make it look better. And then every attempt add 1, you add obstacles, so randomized x, y. And then you check whether it's possible. Remember the inputs. Yes, possible. Goal, obstacles. The goal is grid size -1, grid size -1, because it's 0, 0 to grid size -1, grid size -1. It's 0, 1, 2, 3, 4, 5. It's 6, right? It's not 5. So, and then you remove the obstacle if it's not possible. So now we're going to define the move function, state, action, and grid size. And the org will be to compare later on. Well, it's just saving down the original state. And then if the action is up, then you add 1 to the y-axis value. And then if it's down, then you minus. And here there's another bug where in the elif and the next elif and the next elif, it should be 1 equal sign rather than 2 equal signs, because that would be a true and false, and you wouldn't be able to move apart from up only. And then if the state is in grid size, then you're just going to return, so that means it's valid. And if you're going outside the grid, that's why we saved the original, you're just going to return the original. And then the training, we're going to start with the 4 actions: up, down, left, right. Doesn't matter even if you're at the current position where you probably can't go up, because you learn that it's not good. And the grid size for me, I chose 20. Number of obstacles 200. The grid size means that there are 400 squares, and 200 sounds reasonable, even though it's kind of full. And then the max attempts for creating the grid would be 300. The alpha learning rate 0.1, gamma 0.9, epsilon greedy, so 0.2, 20% of choosing a random action. You're having to initialize the start X, start Y, go X, go Y values. Make goal position a tuple. Episodes, we're going to use 2000. And then you're just going to create the Q table and the obstacle table. Sorry, the obstacles, yeah. And then the bug here is that I added a unnecessary punctuation. And then for episodes in range episodes, each episode you're going to start at start X and start Y, and you're going to reinitialize Vista as a empty set. And then while you're not at the goal, you're just going to keep doing this again and again. You keep moving because it is possible, and if it's possible, there's always a chance for you to go to the goal. And we're not going to have a max attempt on this. And then random between 0 and 1. If it's lower than epsilon, 20%, there's a chance of randomly choosing an action. Else, we're going to have a argmax over the Q state values. And then the next state, it depends on the action, state, and grid size. And we're going to get the reward from the grid reward function. And the old value would be the state action value of your action and your state, basically. And then the future best, which is the max value, yeah. And then now you update it with a old value plus alpha, learning rate, times reward plus gamma, which is a discount factor, times the future best possible value minus the old value. And it's not value function, this is state value function, so state action function. And then you're going to use, in testing here, what went wrong was that I used state equals to list 0, 0, while states are unhashable. You should use a tuple instead. And then this is just testing. Because we didn't have a function, we're going to have to write the loop again, but it's not that much anyway. So the only thing, the thing that we got from training was actually the Q table itself only. And then you're going to print path done generated, and then you're going to plot. So the plot, you're going to have a figure size of 5, 5. And in the grid, you're going to make a horizontal line. And I in range grid size plus 1 is because if you have 5 boxes, you would need to have 6 lines to cover them all. And you just do that for horizontal and vertical lines as well. And now you do this for the same for obstacles. You're going to fill between the coordinates of the obstacles. So if it's here, then you're going to fill X to here, and then the Y, OY to here, right? And then here there's another bug, is where in fill between I wrote FIL instead of FILL. After that, we're going to fill between for the start and the goal. And yep. So that weird 0, 1, 0, 1 is actually just the start, in which you're going from 0 to 1 x-axis and 0 to 1 y-axis. Color blue. Alpha is just how transparent, so 0.3 means you're 70% transparent. And you do the same thing for the goal position. I think you fill in red. Wait, no. Yeah, red. And then the text, S would be start, and 0.5, 0.5 is to make it centered. And then you're centering against the horizontal axis is centered, and the vertical axis is also centered. You do the same thing for the goal. Grid size minus 0.5, because grid size is all the way here. You're minusing 0.5, which is half a cell. And then you minus 0.5, which is half a cell. You do the same thing. And then the font size, font weight, yeah, just your own custom choice. And now we're doing the path outline, in which if we go here to here, then we're going to have this, right? So it makes the visualization better. And it's plus 0.5 because you're centering it in the middle, and instead of just being on the line itself, you're supposed to be in the box. And the AX plot for the PX and PY trajectory, the row dash is actually just what I already said, was a red line with the red little dots on the marks. And now you fit the plot better. So the AX dot set X lim and Y lim is just to make sure that the grid actually fits it perfectly, so it makes it better looking. And in here there's a other bug where I made a set underscore Y lim. It was supposed to be LIM, but I did LIN. So yeah, fix that. And then once you're done fixing that, you're just going to have to do plot.show. I also inverted the y-axis. Use a T, by the way, it's not invert. And then after running, it should run really quick. And then you're going to see a nice grid here. And you can clearly see the trajectory it went. And yeah, 200 was a bit overkill for 20 grid size, but it's up to you. So even if you do like 300, it's possible for it to generate a possible path, and you can play it around yourself. But sadly, this is a square implementation. If you want to do a rectangle or some other shape, then you're going to have to customize the grid size, and the grid size should probably be a list or a tuple, something like that. All right.